Hi, hello, welcome to VHDL Basics. Today we are going to discuss about two-stage flip-flop synchronizer. So first of all, what is two flip-flop synchronizer? A synchronizer typically consists of a pair of flip-flops, often referred to as a two-stage synchronizer. The input data signal from the source clock domain is first captured by the first flip-flop, and output of the first flip-flop is then further captured by the second flip-flop in the designation clock domain. The two-stage capture helps reduce the possibility of metastability by providing the additional time for the signal to stabilize. The two-stage synchronizer is commonly used technique for synchronizing asynchronous signals to a clock domain. Here are some pros and cons of using a two flip-flop synchronizer. Pros: improved metastability handling. So the first two synchronizer reduce the probability of metastability compared to the single flip-flop synchronizer. By capturing the input signal into consecutive clock cycle, the chances of capturing metastability are slightly reduced, significantly reduced actually. Asynchronous to synchronous signal conversion. The synchronizer allows you to safely transfer a asynchronous signal to a synchronous domain without violating the setup and hold time requirement for the of the receiving flip-flop. It helps ensure proper synchronization and avoids data corruption. Simplicity. The two flip-flop synchronizer is relatively simple to implement and understand. It requires only two flip-flops and a few combinational logic gates, making it easy to integrate into the larger design. Moving to the cons. Increased latency. Due to the double synchronization process, the two flip-flop synchronizer introduced the additional latency compared to the single flip-flop synchronizer. The output signal is delayed by two clock cycle, which may impact real time or real sensitive application. Limited metastability handling. While the two flip-flop synchronizer reduces the chance of metastability, it does not completely eliminate the possibility. In rare cases, if both flip-flops capture a metastability state simultaneously, there is still a small probability of propagating the metastability value further downstream. Power consumption. Since the two flip-flop synchronizer requires a additional flip-flop, it consumes more power compared to the single flip-flop synchronizer. In power sensitive design, this increased power consumption may be a concern. It's important to note that choice of synchronizer design depends on the specific requirement and constraint of your system. Other synchronizer architectures such as synchronizer with high number of flip-flops or gray code based synchronizer may offer different trade-offs in terms of latency, metastability handling and power consumption. So this is the circuit diagram of two-stage synchronizer. So first, if output of the source clock domain is connected to the input of the first flip-flop in the synchronizer. Here that is referred to D in. Then the output of the first flip-flop of the synchronizer TS is connected to the input to the second flip-flop of the synchronizer. So these two flops are implemented using the receiving clock domain. And this D out we can use in our the actual logic. After synchronization is done, we can use this D out in our next logics actually. So this is the waveform for the two stage synchronizer. So this is clock A, this is source clock. Clock B is the destination clock or receiving clock. So D in with respect to clock A, it is rising edge at the time of rising edge. So if this is falling into the setup for old violation of the clock, old time of the clock B, then we will get the metastability state for the first clock. Then next clock it will stabilize, right? So then the next flip-flop will capture this DS and it will give the proper D out output here. So this is how we can reduce the metastability and we can get the stable output here. Now I am going to ask ChatGPT to write a two-stage flip-flop synchronizer. So design a two-flop synchronizer in Verilog actually. So once this ChatGPT is generated the code, then I will try to simulate that one and I will explain with the simulation waveform. So this is the synchronizer which ChatGPT is generated. So here if you see a clock and reset and data in are the input and data out will be the output. So here in ChatGPT they are trying to have 2-bit synchronizer bit registers actually, but here if you see it is implementing three-stage flip-flop actually. So first data in will be assigned to synchronizer register 0th bit, and then it will be assigned to the next clock pulse. It will be assigned to uh, first bit of the synchronous register. The third clock pulse, the first bit of the synchronous register will be assigned to data out. So it is implementing three stage flip-flop here, but I'm going to change this code to make it to make two-stage implementation, two-stage flip-flop implementation here. So for that I'm changing like this. So I'm reducing the width of the synchronizer register. So now that is single bit synchronous register. When it is reset, I am assigning that to 0. When reset is deasserted, the data in will be assigned to the synchronous register for the first clock pulse. The next clock pulse, the synchronous register value will be assigned to the data out. So here, if you see, there are two flip-flops are implemented here. This is the test bench for this particular two-stage synchronizer. Since reset clock data in our input, I am declaring that as register and data out is the output. So I am declaring that as well, that as wire actually. And then the the initialization of the synchronizer line number 5 to 9, I am doing that. In the initial block, I am toggling reset and data in and declaring initiating the clock. And in the always block, I am generating the clock actually. So moving to the waveform so that we can understand more on the two-stage synchronization. So here if you see this is our designation clock and this is the reset of this particular synchronizer and this is the input of this synchronizer and this is the output of the synchronizer. If you see so once reset is released then data is going high but here we are using passage of the clock to sample the data in. So here only it will take. So here in this clock pulse, if you see the synchronous register is going high. So this is first flip-flop output. Then if you see the second flip-flop um, will be giving the output in this edge. So if you see this is the D out. So here we are getting the D out which is after the two flip-flop implementation. So this is synchronized with respect to this clock. So this is how we need to implement the two-stage synchronizer. Thanks for watching this video. Please like, share and subscribe this channel for more videos.